Hey guys, welcome back to Car Academy. In this series of video, we are looking into NVIDIA Cuda programming. Today we are going to take a look at the implementation of the addition program using parallel computing in GPU. So in the last couple of videos, I explained about grids, blocks, threads, etc. So if you want to learn about that, if you want to understand about grids, blocks and threads, please go and watch the previous videos. So the concept of today is basically array addition in GPU. So for that, what we are going to do is basically we are going to do a one-dimensional array addition. So here basically you are given two arrays. Okay, so two arrays of same size. So let's name that two arrays as array A and array B, both having n elements. Okay, so basically the arrays look like this. So you have 0 1 indexes till n minus 1. Okay, so let's say this is array A and you have another array B with the same indices 0 to n minus 1. So basically these are two source arrays, and what we will be doing is basically you have another array with same number of elements 0 to n minus 1. This is array C, which will hold the result of the addition. So this will hold the result. So basically what happens is you are going to do addition of two arrays and storing the result in array C. Now let's go and take a look at how we basically can do this using GPUs. Okay, so for that what I will be doing is we'll have to use the concept of threads, grids, blocks. So for the simplicity, you can think basically something like each grid will have some two-dimensional blocks. Okay, and each block will have certain number of threads. Okay, so some GPUs will have 256 threads, some GPUs will have 512 threads, some GPUs will have 1024 threads. Okay, so in this program let's assume that our each array is 128 elements wide. Okay, so what we can do is basically since this is a one-dimensional array, we can use just the thread index dot x to differentiate the threads. So we will be basically using thread index dot x to differentiate or to address the different parts of the array. Okay, so here you have 0 to 127. So what we can do is basically you can use a kernel with just one block. Okay, and with 128 threads. Okay, so that's what we are going to do, and for that we'll also have to do something. So remember that anything that we basically allocate in the CPU. So there are in the previous video we also learned about device memory and also the host memory. So there are two types of memory. Okay, so one is host memory and other one is GPU memory. Okay, so GPU can access only the GPU memory, also called as device memory. So you have array A, you have array B, and you have array C. Okay, so these arrays allocated in the DRAM cannot be accessed by the GPU. So what we will have to do is we will have to allocate similar array in the GPU memory or the device memory. So there is a separate API available to allocate memory in GPU. So for host, we use something called malloc to allocate memory. In GPU, if you have to allocate, you have to use CUDA malloc. Okay. Now what happens is once you allocate and fill these array, we will have to copy the contents from the host memory to the GPU memory. Similarly, once you fill the host memory, you will have to go and fill the GPU memory. Now what happens is the GPU is going to perform the addition. So the result is actually filled here. Okay, so this device memory result will have to be copied back to the CPU. So for that, basically to copy from the host to GPU and also back from GPU to host, we use the API called CUDA memcopy. So in CPU, we use API memcopy to copy from one memory location to another memory location, whereas in CUDA, to copy from GPU to CPU or from CPU to GPU, we use a API called CUDA memcopy. So that is what we are going to use in this program. So let's go and write this program. So let me quickly okay, so let's go and write this program. So we will have to use CUDA runtime.h. We will have to use IO stream for including all the std out. So now let's go and write the kernel. The kernel is very simple. So we write the kernel using the global keyword, and let's say this is add array kernel. Okay, so now you have, let's say, int a, int star b. These are two different source arrays, and here let's say n. That's basically the number of elements. Okay, so now what we will be doing is, so we'll have to perform the addition here. So addition can be performed by basically you just need the thread index. Okay, so the thread index can be found using the thread index.x. Okay, so we're just going to use the thread index.x. Since it's just a one-dimensional array, let's just use the x component, and what we will be doing is c of index is equal to a. Okay, so we are using the upper letter c. C of index is equal to a of index plus b of index. So that's all we are going to do. Okay, so basically what happens is each thread is basically going to operate on different parts of data in array A, B, and C. So now let's go and write the main program. So in successful case, you return 0. Now what we will be doing is, so this is basically CPU A, CPU B. These are the CPU arrays or the host memories we will have to allocate, and this is the memory we use it to store the result of the GPU. Or what we will do is we will CPU result, we will GPU result. Okay, now you also need GPU memory. For that, GPU B, GPU C. Okay, now in order to fill, what we will be doing is, so first we'll have to allocate the host memory, I'm not going to basically check if the memory has been allocated properly or not, so I'm just assuming that. Okay, for this program I'm going to let's just define the size here, 128. N is 128 here, so n times size of int. So I'm allocating memory for CPU A, CPU B. This is the host memory. Size of int. We'll also have to allocate memory for the result, n times size of int. Okay, now we'll also have to allocate memory for copying the results back into the CPU. So this is basically CPU computed result. This is GPU computed result but copied back to CPU. Okay, we'll do the copy later. Now allocate the device memory. Okay, so here let's check, because sometimes the GPU uh, won't be available. So what I'm going to do is I'm going to allocate the GPU. So for that you will have to use the address of the pointer. So you will have to typecast to void star star, and here you will have to give n times size of int and check if this has been successfully allocated or not. Okay, so in case if this is not successfully allocated, you print error allocating GPU A memory. Okay, so then just return some error code. For now I'm just returning -1. You allocate memory for the GPU B or the B array in the GPU n times size of int not equal to Cuda success. So just go and print if there is any error or if there is any failure in in allocating the GPU. Error allocating GPU B memory. Then just return -1. Now let's allocate memory for the GPU or GPU C, which is also the result memory. Cuda success. You can also print it using cout, but this will clearly tell you if you use C error, you can basically differentiate normal messages versus error messages. So there is a separate way to basically just extract the error logs from the program output. So that is why I'm just giving std cout. We will also have to free all the memories allocated. So I'm first freeing CPU. We will have to write our logics in between the allocation and the free. So instead of, sometimes we will just forget the allocated memories and that will become leaks. So as soon as you allocate memory, just also write code for deallocating the memory. So C++ smart pointers helps us to achieve this automatically, but since you're using the C style APIs, we'll have to do manually. So in order to deallocate or free the GPU memory, you have to use CUDA free API. Okay, GPU B. Now let's free up the GPU C. Okay, so these are the memories that we allocated. Now what we will have to do is basically, let's list down what we should do. Basically now initialize CPU arrays A and B. Then we'll have to copy A and B, copy CPU A to GPU A and CPU B to GPU B. Perform, this is basically the high level algorithm. Perform addition in CPU, then perform addition in GPU, then basically copy the GPU result back to CPU. Okay, so let's go and write this code. Now initialize this array. So what we will do is int I is equal to 0, I less than this n I plus plus. I'm just going to initialize with some numbers. So here what we will be doing is CPU A, I'm just going to basically assign I. For CPU B, I will just allocate I plus 1. Okay, now we have initialized this. You can initialize with whatever value you want, since this is the easiest way to check the result in case if there is some error. We'll be able to understand what value we assigned and what the result should be. Okay, so now we have to go and copy. So for that, I'm using CUDA mem copy. So for mem copy, I will have to use GPU A, which is basically the target memory, and also will have to specify the size here. And finally, how you have to copy. So here we'll have to specify CUDA mem copy. We are going to copy from host to device. So this is important. Okay, if there is any error, let's just print error copying CPU A to GPU A. Okay, let's return -1. We'll have to basically free the memory. I'm just ignoring it for now, but if you're writing any production level code, you will have to free the memory. Okay, GPU B, CPU B, n times size of int CUDA memcopy host to device. So just print the error message here. Error copying CPU B to GPU B. Okay, now what we will have to do is, let's also copy the GPU result back here. We know the API CUDA memcopy. So we'll have to copy to GPU result from GPU C, sizes n times size of int, comma CUDA. Just remember that now we are copying from device to host, so we'll have to specify here CUDA memcopy device to host. CUDA, if it's not success, basically if something happened to the copy, we will get other than CUDA success. So C error copying GPU C to GPU result. Return some error code here. We're just returning -1 here. Now we'll also have to basically verify the result. Okay, let's write the code. Before we copy, we'll have to make sure that all the threads has completed the operation, which will be confirmed by calling the CUDA device synchronize. So basically we'll have to ensure that all the threads has completed its operation by calling the CUDA device synchronize API. So let's go and perform addition. So for int I is equal to 0, I less than n, I plus plus. So here it's pretty straightforward. We will have to just C of, or not C, this is basically CPU C, or that's not CPU C, that's basically CPU result of I is equal to CPU A of I plus CPU B of I. So that's all. This is pretty simple. We'll have to basically add all the elements in CPU. Now let's perform the addition in GPU. This is also pretty straightforward. So add array kernel. Now in this case, we are just using one block, but the number of threads, since the number of threads is like less than 1024, we will just use n threads here, and here we will have to call this kernel using the three different GPU arrays or the device arrays. Now we'll also have to pass n. Okay, so once this is done, so basically what we have done is basically four parameters we passed: a, b, c, and n. Here you can see, oh, it's not GPU result, it's basically GPU C. We will have to pass GPU C. GPU result is basically the result array stored in CPU. Okay, so GPU C. Okay, now let's go and compile this and see. Okay, so there is a error, CPU C. CPU C, that's not CPU C, that should be CPU result. Let's go and change that. And that is the only compilation error. Okay, so you write a big code and just get one error. Okay, there's one more error. Free CPU result. Okay, let's see if there are more errors. Okay, no more errors. What we haven't done so far is we haven't verified the results. We just performed addition in CPU and GPU, but we have not performed the. Now what we will be doing is we'll have to check if all the results in all the elements in the CPU and GPU memory is same. If CPU result not equal to GPU result, okay, so let's, in this case, let's print error in addition at location. Let's print the location and CPU. What is the CPU result? GPU. Let's print GPU result of I. Okay, so we made a bug here. We'll have to specify GPU result of I. Similarly here, CPU result of I. Okay, now let's go and run this. If there is any error, it should print. Okay, so we did not get anything. Now what we will do is, okay, so if there is any error, what we can do is, let's just return here if there is any error. If not, let's go and print std cout GPU addition completed successfully. Okay, let's print this message so that we get some confidence. Okay, so you have seen basically here we use 128 threads. Basically we have two different arrays, CPU A and CPU B, both having 128 elements. We allocated that using malloc. We stored the result in the CPU result array, again allocated with n elements. GPU result is basically a memory that holds the GPU result after the addition is performed in the GPU. Okay, so we also allocated the device memory, which is also the GPU memory. Then we initialize the CPU arrays. We copy the same data to GPU using CUDA mem copy. We perform the addition in CPU using this for loop. We perform the addition in GPU by calling the kernel with n different threads. Okay, so this is important. We can also do the addition in the GPU using a for loop. So in the next video, I can show you how to do the same operation in GPU. Okay, so then once the addition operation is completed, that's basically ensured by calling this CUDA device synchronize. So once the addition is performed or completed, we will be basically copying the GPU result back to the CPU memory. The CPU cannot access the device memory or the GPU memory. Similarly, the GPU cannot access the CPU memory or the host memory. So we'll have to basically copy the data back and forth. So once we get the GPU result in CPU, we are comparing the CPU computed result versus the GPU computed result. If there is any difference, we will print this error message. We'll say there's some issue at this particular location, there's some discrepancy between the CPU result and the GPU result. If there is no issue, we will print GPU addition completed successfully message. Okay. I hope you like this video. Subscribe to this channel, share it with your friends. I hope you learned something new in CUDA programming today. I'll be explaining more using different techniques. Basically, we can do the same addition operation, parallel computation using a for loop in the kernel. We can also use multiple blocks to perform the addition, parallel computing addition. So this works with single dimension because our array size is small. If the array size is huge, let's say you have like 10,000 elements or 100k elements, we cannot do that with single just thread indexes. Okay, so we'll have to use block indexes. We'll see how to do that in the subsequent programs. So hope you like this video. Subscribe to this channel, share it with your friends. I'll record the next video as soon as possible. Till then, signing off, guys. Bye.